Okay, perfect. So I will move forward. You have here my email address in case you have any contact. I'm going to show you the hierarchy of odor control strategies. What we should do actually, it's start by but designing prevention, odor information and emission strategies. If we cannot do that, we can try to control the dispersion and to minimize the impact when the odorants are nearby the population. And if nothing can be done to prevent formation emission or to minimize impact, then we need to go for end of the pipe treatment. The potential for odor nuisance increases when we go up in the pyramid, and also the treatment cost decreases when we go up into the pyramid. In this presentation, I will focus on preventing odor formation and emission, and in end of the pipe treatment technologies with new advances to improve the abatement of biotechnologies. Okay, so focusing on prevention of odor formation and emission, we can focus in this context of wastewater treatment, wastewater sanitation, on the sewer networks, where we need to minimize the residence time to avoid odor formation. Try to design gravity settlers that allow for a natural oxygenation with oxygenation rates that prevent septicity up to 20 milligrams per liter per hour in the liquid running into the sewer network. We can design oxygenation strategies in key transportation points of the sewer networks, or we can even dose chemical nitrate or ferric salts to prevent septic conditions or to precipitate hydrogen sulfide. Within the wastewater treatment plant, we just need to be careful with the frequent cleaning of screening and grid to prevent accumulation of organic biomass that deteriorates. Frequently clean the bottom of the primary settlers, minimize weirs and hydraulic drops to prevent odorant release, avoid overloads of aeration tanks, also by designing proper mixing and aeration strategies, and minimize the sludge accumulation in thickenings and underwater units. We can also go for more innovative strategies based on recirculation, some of the byproducts from wastewater treatment, such as the recirculation of the headworks, activated sludge, recirculation to the headworks of the activated sludge, either directly from the aeration tank, okay, the nitrification tank, or from the settled biomass in the secondary settler. The introduction into the headworks of biomass fosters the absorption and oxidation of volatile sulfur compounds, volatile organic contaminants, and volatile fatty acids. Okay, the activated sludge contains some dissolved oxygen. Concentrations can be high depending on whether we take it from the activated sludge tank or from the settler, and this activated sludge has a high microbial diversity. On the other hand, we can recirculate an electron acceptor different than oxygen, which is nitrate or nitrite, which supports anoxic odor formation. So we can either recirculate the nitrate produced from the oxidation of the liquid diastase, from the watering of the diastase produced during anaerobic digestion of primary and secondary sludge, or we can directly recirculate the mixed liquor from the nitrification tank. In any case, nitrate acts as an electron acceptor to support the oxidation of odorants. This is an example in enclosed bottles supplied with 100 milliliter of fresh activated sludge, where we monitor the removal of H2S over time, and using either nitrate or nitrite as electron acceptor. You can see that when increasing nitrate to 10 milligrams per liter or nitrite to 10 milligrams per liter, hydrogen sulfide in the headspace decreases sharply within a couple of hours, which shows the potential of this technology. Okay, by combining activated sludge recycling with nitrate or nitrite recycling. In any case, nitrate was more effective than nitrite in terms of H2S removal. If we cannot prevent odorant formation, we can go for end-of-the-pipe treatment technologies. Today, there is a large portfolio of technologies at commercial scale, from conventional chemical scrubbers, ozonation units, activated carbon, or incineration units. And today we have biotrickling filters, biotrickling bioscrubbers available and effective at commercial scale, and activated sludge diffusion in wastewater treatment plants. If we analyze the operating costs, we can see that biotrickling filters exhibit the lowest operating costs, down to 1.2 euros per cubic meter per hour of design capacity per year. Biofilters exhibit a slightly higher operating cost, mainly due both by technologies to the frequent replacement every 2 years, every 5-10 years of the packing material. However, these operating costs are lower than chemical scrubbers or activated carbon filters, with the operating cost 3 to 6 times higher due to the need for a replacement of activated carbon or purchase of chemicals during chemical oxidation. In order to improve the performance of biotechnologies, we can modify the process, the design, and I'm going to show some examples of enhancement of biotechnology. The first one is two-phase partitioning bioreactors to improve the robustness and VOC mass transfer. For those of you that don't know two-phase partitioning bioreactors, they are based on the addition to the bioreactor of an immiscible, non-volatile, biocompatible, and non-biodegradable organic solvent with high solubility for the odorants. We can have silicone oil or other solvents, and two-phase partitioning bioreactors can be implemented in any bioreactor configuration, from biotrickling filters, airlifts, fermenters, or Taylor flow reactors. By adding a secondary non-aqueous phase, we create a new and efficient pathway for the transfer of the odorants from the gas to the liquid phase, where microorganisms are. We increase process stability, since the organic phase has a high capacity to absorb contaminants, and which acts as a buffer. And also the presence of the organic phase increases the gas-liquid interfacial area. I'm going to show you some examples of how two-phase partitioning bioreactors implemented in biotrickling filters can increase their robustness. Okay, here we tested the biodegradation of 4 different VOCs, one very soluble, butanone, moderately soluble, toluene, and poorly soluble like pinene and hexane. And what we did is assess a conventional water phase biotrickling filter compared with a two-phase biotrickling filter constructed with silicone oil. We increase pollutant concentration by a factor of 3 or by a factor of 6, and monitor the concentration in the biofilters in the outlet. And you can see here that the two-phase biotrickling filter in yellow triangles was able to maintain very low concentrations of toluene, of pinene, even when the concentration of pollutant increased by a factor of 6. Hexane, which is the most hydrophobic pollutant, was also more effectively degraded during the pollutant surges in the two-phase partitioning bioreactor compared to the conventional water phase. This technology is being scaled up right now in a few cubic meter biotrickling filters, treating 1,800 cubic meter per hour of a real odor stream in Barcelona waste treatment plant. We are also doing some research on engineering of more sustainable and efficient packing material, particularly turning plastic waste from the wastewater cycle, which could be also from a waste treatment cycle, into novel carrier materials, where the plastic are melted and extruded in novel packing materials. Here I'm showing you some of the results we did with our extruded recycled plastic material printed with 3D compared to recycled plastic material, which is the lid of the plastic bottles, and compared to commercial plastic rings, using model contaminants like H2S, ammonia, toluene, and painting at different gas residence time. H2S and ammonia were fully degraded at the 4 gas residence time, tested even at 6 seconds, and when assessing the performance of the packing material for volatile organic contaminants, we see that the biofilter with the extruded plastic recycled material perform better with both toluene and painting. And finally, some other technologies to be implemented in biofilters or biotrickling filters, which are based on bioactive coating, which are based on engineering the biofilm with polymeric coating like latex in order to create a very dense population of active degrading cell in resting state. The packing material, this latex, has high affinity for VOC, which enhances the mass transfer from the gas phase. And this is a technology that can be engineered in pack-bed configuration. I'm showing you here some preliminary results from a test we did with a biofilm on a water phase agarose and in latex. And you see here that the specific elimination capacity of toluene was much higher when using a latex-based bioactive coating. As a take-home message, prevention of odorant formation can be cost-effectively achieved within the wastewater treatment sector at minimal operating and capital cost using activated sludge or ammonia oxidation recycling technologies. End-of-the-pipe biotechnologies exhibit lower operation cost than physical-chemical technologies and similar effectiveness in odor abatement. Two-phase partitioning bioreactors show a superior abatement and robustness during treatment of hydrophobic VOCs. And we can engineer new packing materials manufactured from residual plastic using 3D printing, and we can also add some iron salts to improve the performance. So that's all from my side.
Many thanks, Raul.
You're welcome.
For the curious insights about innovative technologies for the odorants and VOC removal from gaseous fluxes. So many thanks for your work and many thanks for a Swiss approach to respect the time schedule. Laura, did you add any info about the advertisement?
Yes, it should come now. We should now have a sponsor announcement, but after the questions. So it would be nice if we could first use a couple of minutes to ask Raul and Sophia in case questions also for the previous presentation. And then we will have this sponsor announcement from IEEE.
Oh, I see that from the chat.
It will take probably some time, you know that we have some delay regarding the question. So Marzio, maybe you have some questions.
I have one, Raul. I've seen that you tested different kind of B-phase treatment in which, for example, you are using biotechnologies but adding some kind of silicone oil or similar. I've seen that you tested the empty bed residence time and the removal efficiencies in the different situation. My question is if you tested, let's say, the saturation itself of the solubility of your tested VOCs within, for example, the silicone oil or anyway the organic phase within your system, without considering the biological contribution.
Okay. Yeah. I mean, there is always a physical absorption and solubilization, but then the pollutant that is absorbed then is gradually degraded, either released back into the aqueous phase or we have seen that some microorganisms can grow at the interface of the silicone oil and uptake the pollutant. So at the end, there is a real biodegradation. It's not just a physical. When there are peaks of pollutants, then there is then there is an absorption, and the lipid phase, the non-aqueous phase, retains the pollutant, but then it's gradually released. It's basically like in an activated carbon system that acts as a buffer. Mm-hmm.
Great, many thanks.
Many thanks. We have one more question from Carlos that should come on the chat, but he sent me. And the question is if there is any commercial producer of two-phase biotrickling filters, or whether it's just at a research stage for the moment.
I mean, it is still a research stage, although we are testing like a 4 cubic meter biotrickling filter to validate the technology. I think after the live Abatement project, the technology will be ready to be uptaken by the market. So it's close because, the main mechanical elements are based on biotrickling filtration. So it will be readily implemented.
Okay, thank you very much.